Hey everyone! I'd like to show you how to design and build a custom machine learning model from scratch that can run live on your phone right now, and it predicts the segmentation mask and four corners of populated chessboards. And it shows that on the screen all in real time. This is a surprisingly difficult and interesting problem. If we can solve this, we can actually solve a lot of similar kinds of problems in the real world. Let me explain. I think you'll find this quite interesting. When our phone camera sees images, it sees RGB pixels on a grid. When it's looking at real chessboards in the world, we want it to find the chessboard in it, meaning not just which pixels belong to the chessboard, which is a segmentation mask, but also how it's positioned in 3D space. We can estimate this 3D pose using the pixel coordinates of the four corners of the board. Let's go through the steps together of researching and designing an ML model that can do all of this from scratch, and I'll try to explain common building blocks and terminology used when building models, such as DNNs or feature pyramids, skip connections, regression or heat maps, and anything else that comes up along the way. My hope is that by the end of this video, you'll have an intuitive understanding of each of these models, and especially how mixing and matching different ML concepts, like attention gates, can improve the base UNet model from the last video. And the most important part, I think, is that you should also get a feel for what it's like to do machine learning research and development. This includes developing things like datasets, model design, loss functions, and the balance between model size versus speed, especially when it comes to web apps. So why are we looking for chessboards? No reason really, besides it being fun and easy to visualize. The important thing is that the techniques used here can and are used in all sorts of real-world use cases, like seeing cars on roads, robot arms in warehouses doing pick and place, medical image segmentation, the list goes on. I use many of these approaches in work. In fact, you're likely already using these models on your cell phone whenever you take a picture. Finding any chessboard in a real-world image can actually be pretty hard, because there are many different types of chessboards, and they have many different styles of pieces on them blocking the view of the board. There's also hands in the way, weird lighting and shadows, confusing environments, and more. We also want this to run in real time, so it has to calculate all of this in a thousandth of a second. This is a surprisingly good analog to other real-world kinds of problems, like when self-driving cars are trying to see pedestrians and cars in the environment while driving. People are wearing different clothes, the lighting is different, they may not always be fully visible. You see the resemblance? If the problem were simpler, say just one style of board and pieces, in the same place with the same lighting every time, or we were to spend 10 years on it, we could use classic computer vision instead, and I did in part 1. But now we have machine learning, and lately it can learn to abstract and generalize quite well, often better than handcrafted algorithms. So what will our model take in? We're going to use 128 by 128 pixel images, partly because it's a pretty common size in existing datasets like ImageNet, partly because 128 is a power of 2, making it easy to divide by 2 multiple times without weird rounding errors, something that several blocks of our model will probably do. But mostly because it's the summer, and I don't want to train the models on my PC for so long my apartment catches on fire. Machine learning models need a lot of good quality data. It's often more important in machine learning research than the actual model design. To get this image dataset to train the model on, I use a 3D modeling software called Blender to design a couple chessboards and pieces, and then wrote a script to randomly place those pieces on the board, vary the lighting, and then take pictures of it from many different angles. We'll use this to train the model, and then we'll test it on a variety of real-life images of chessboards. The reason I use synthetic data is because I want to have good labeling of the data, meaning knowing exactly where the corners of the chessboards are, which pixels in the image are a chessboard or pieces, a good coverage of all the different kinds of chessboards and different positioning of pieces blocking the view, and different places and lighting and so on. In a perfect world, I would have thousands to tens of thousands of real-life images of chessboards where someone, probably me, has manually labeled all this extra information. It sure would be nice if synthetic images were enough. And the good news is it turns out they are. And the beauty of synthetic data is we can generate as many images as we want. So let's generate 10,000 images. It takes about 10 minutes. And it places pieces off the board too. Let's also augment our images by adding random backgrounds, and then we can randomize the image by augmenting it with warps or color changes, and so on to help the model generalize for real images. What should our model output be? To tell which pixels are chessboards, we can train the model to predict a new grayscale image, where the pixels are either white or black as ones and zeros. This will be the segmentation mask. How do we get the four corners or key points of the chessboard though? We could try to predict the XY coordinate numbers directly. This is called direct regression, and I really wanted it to work. I've spent an inordinate amount of time trying this ever since the part 1 video. The long and short of it is that the model sizes get huge before we even start to converge a little, and the precision is still lacking. It just needs so much data. This is a common dilemma of direct regression versus heat map-based models when it comes to key point detection. It's still an active research field, and generally the vision architectures we are looking at struggle spatially unless it's intrinsic like a heat map. I had started building a CenterNet version, which uses ImageNet as a backbone, modified to learn layers of corner offsets, and this was a promising alternative to direct regression, but it's not there yet. I really do want to come back to this at some point, once I have more satisfying results. Instead of directly predicting the corners, we could try and predict images where only the pixels at the corner are white, kind of like a bastardized segmentation mask. Let's make our model take in an RGB image and predict 4 heat maps and a segmentation mask, all 128 by 128 pixel sized. And by the way, we usually call large matrices of numbers with multiple dimensions like these tensors. I sort of interchangeably use words like image map, mask, heat map, and tensor throughout the video, but really it's all just large grids of numbers. For the corners, if we only score the 1 pixel as a corner, the model doesn't get any feedback on if it's close to a corner or not as it guesses. So instead of a binary 0 or 1, we could use a Gaussian blurred hotspot instead, which is a common technique that makes these models much easier to train. It kind of gives guidance that guesses near the corner are better than far from the corner. There are a lot of model architectures out there, which consist of different building blocks that can be combined in different ways to make a custom model. Sometimes it can be large language models you may have heard of, like ChatGPT, Gemini, Llama, or DeepSeek. Models like these started out as text in, text out, with quite a lot of building blocks in them, and many of them are multimodal now, meaning they can take in or put out data that isn't just one kind like text, but could also be images or videos or audio or some combination thereof. Kind of like Google DeepMind's VO3. For our use case, we're taking in images and putting out images. Some existing models based around ImageNet are a good starting point for these ideas, or even as a backbone. Alright, so we've got our idea, image in to image out of heat maps and segmentation. Let's start designing a model architecture. The simplest network we could try is a dense neural network, or DNN. These connect all the values to all the other values in a layer, and we usually add a nonlinear block like a ReLU on the end too. The problem with dense connections is that there's too many of them. If this was the classic MNIST handwriting problem with those tiny 28 by 28 grayscale images, we'd have a chance because you could string together a couple DNN blocks together and get a working model that isn't too large. And look at this, the DNN is predicting numbers from handwritten digits. But for our 128 by 128 by 3 RGB images, the number of connections for even one block with, say, 16 features would blow up to billions of parameters immediately. And we'd still need more blocks to make this model learn anything. So we're going to have to keep on looking. Instead of DNNs, we could use convolutional neural networks, which instead of multiplying everything with everything, it instead only learns a small window or a filter that slides through the input tensor, and this process is called convolution. Things like blurring or sharpening images in Photoshop do this based on the type of filter, and our model will learn these filters. So this makes the model size a bit more reasonable, but because we're using a small, say 3 by 3 window, each pixel only knows as much as what's next to it, which makes it pretty hard to tell what a chessboard is because it's now lost track of the overall image. If we were to add more layers or more CNN blocks, these deeper layers can get the previous context filtered through it, essentially getting a bit more spatial information. However, each block only increases that window size linearly, so let's say you had 2 layers, you'd get a 5x5 block, and then 3 layers a 6x6 block or 7x7 block, and so on. So you'd need around 127 layers for the pixel all the way on the left to have context for a pixel all the way on the right. Alright, the model is about 6 megabytes. Let's train for 20 epochs. Hey, this is an improvement over the dense network. It's starting to identify chessboard-like areas, but it has a hard time with the noisy background still. Which makes sense because it's limited by spatial context. We'd have to add a lot more layers, so let's keep looking. Early on, one of the first models to tackle this scale issue was AlexNet, which started using max pools to scale the image down. This is an efficient way to get that spatial context back, as now that 3x3 window covers twice as much spatial distance. If we do this a few times, we can quickly cover most of the image in only a few layers. Of course, you're losing fine detail as you scale down. So what's sort of happening here is as the layers get deeper and the image gets smaller, the model is getting more and more spatial context with less and less fine detail. Alright, for our feature pyramid network model, we'll add convolutional layers as well as max pool layers, and we'll do it about 6 times. And then we'll train the model for 20 epochs, and let's see what we get. Wow, it looks like it's actually started to figure out where the chessboard is. We're getting pretty decent segmentation as well as starting to get the corners. The red lines and circles show the peaks of these heat map corners, and it's actually getting around where the chessboard corners should be. So this model is working really well. I'm really happy to see that, and it's not too big yet. However, as you can see, it's pretty coarse. This is going to be too coarse to be a useful model as is. And though it can sort of learn that corners are near each other at this low scale, we want precisely where it is too, at the original scale. To get that resolution back, we can scale the image back up in reverse of what we did before. This architecture first came about in a paper on medical image segmentation, and though it seems pretty obvious now, it was pretty revolutionary at the time. Let's look at the main building blocks. We have convolutions paired up, which we'll call CoordConv Blocks. We have a max pool to scale images down by half size, and we have up convolutions to scale those images back up, doubling their size. Putting it all together, we see this creates a U-shape, hence the name UNet. So thinking about what happens here, we get our correct scale image with enough spatial context in the image, and without using an insane number of parameters. You may notice a problem here though. We're scaling down to a small resolution, and then scaling that back up. But all that information has been squeezed into this bottleneck, and just like upscaling a tiny image, the fine detail is lost. To fix this, we can add skip connections, where we can directly pass along the results from the layer at the same scale to the other side. This passes along the fine detail information, and then merges that with the wider context from lower layers. And with that, whoa, now it's starting to work really well. The model's not too big, and we're getting some good segmentations. Heat maps still have some issues. Now we're starting to get some interesting visual results. I want to get a sense of how fast or slow these models will actually run on mobile devices. Profiling is king, obviously, but now is a good time to export these models into a format any device could run, whether it's a PC or a cell phone or even a robot. And then we can see directly how fast a model actually is in a tangible, real-time way. Let's open up an editor, and I'll make an HTML page with JavaScript that uses TensorFlow.js with WebGPU. TensorFlow.js is really well optimized for running inference models on the GPU through the web, and it's one of the reasons I tend to use it over PyTorches like ONNX or Onyx models. Alright, so thinking about the code, I want to be able to see a live camera feed from my phone, and we'll overlay the prediction segmentation mask and heat maps on top of the live feed. We can color each corner differently, similar to how we did it in training. This should be simple.
A few moments later.
Okay, I've got a basic web page showing the camera feed, and I'm loading the model correctly. This was a lot of fun to make. I actually used Gemini to get an initial demo up quickly. It got me here super fast. Alright, so now it's displaying, but for some reason, even though the model predicts in milliseconds, it's taking 10 to 100 times longer to load and display it on its screen, kind of limiting my FPS to like 10 to 15 FPS. Looking at the profiler, I see part of the problem is moving the results from the GPU back to the CPU is the bottleneck. Really, I want to just draw it live on the screen, which is a GPU process, so there should be a way to do that without having to go through the CPU first.
2 hours later.
Okay, this was a rabbit hole. I'll admit, web dev with asynchronous JavaScript operations and TensorFlow and WebGPU, it's not my forte. But look at this, it's running in real time now. On my desktop, it's comfortably running at 120 FPS, which I think is my monitor refresh rate limiting it. Looking at the Chrome profiler, the entire animation frame is only taking like 3 or 4 milliseconds. I had several memory leaks in my initial code, which I patched up with a healthy dose of tftidy. That handles managing garbage collection of tensors automatically. I also kept everything on the GPU using TF Browser Draw and having all the processing and drawing to canvas happen in TF Tensorland, where it stays on the GPU. Let's add finding the peaks of heat maps and draw them in as a little box, with yellow lines between them, outlining the chessboard in real time. And let's also add a simple XY axis overlay, which I think looks pretty cool, and it's a precursor to all the 3D pose stuff. Oh, this is awesome. Being able to run it live on a web browser makes debugging and testing the feel of this model way easier. I can also play around with the edge cases like this in real time to find the limits. It's quite satisfying. Another nice thing about it is I can compare the performance of the frames per second on my phone between the different models I trained. Let's think about different ways one could improve on this. Some things to think about are improving the model architecture, improving the dataset, improving the training process, and improving the loss functions. There's more, but let's start with that. I think we can improve on the spatial context by upgrading our UNet to take in skip connections, not just from the same layer, but upscale from lower layers and merged. This architecture with a pyramid of extra connections is called the UNet++ architecture. And while it sounds a little bit more complex, we can write some extra loops in our code to generate these programmatically. Adding these extra connections gives us a lot more spatial context without too many more parameters. It even allows us to drop the number of filters in the more expensive parts of the model. This sort of tuning of filter sizes and layers is something I'm doing manually here. For example, I train the model for some fixed number of steps, and then I get a testing loss. I can try more filters to get better, but see that it's slower now. Then perhaps make the UNet have more depth layers, or less. And slowly I kind of work my way to a relatively optimal combination of parameters in a process called hyperparameter tuning. I'm doing this manually, but in a production setting, one could and probably should automate this type of testing process once you've settled on an architecture. Next, let's have a look at our dataset. One thing I noticed in the previous video was that the model sometimes predicted the board where the pieces were, even when the pieces are on the table next to the chessboard. This sort of makes sense, since in our dataset, the only time we ever saw pieces was when it was on the board. So the model probably started to learn this idea that where there are pieces, there is a board. This isn't always true, and in real images we can see that they often place the taken chess pieces on the side of the board. So let's modify our dataset to also have pieces outside the board. In our Blender script, I can add a function to take the pieces that aren't on the board and place them off the board instead, just like a real game. Since we're choosing piece positions based off of real games, this does a pretty good job of making a distribution of images similar to real life. Another thing we can do is add some more image augmentations in the training pipeline. We can add random shadows that are similar-ish to real life like this. I also found adding random motion blur really helps the model work with video and phone footage, so we'll add that too. I then tried smaller and larger Gaussians for the training data heat maps to see how it would affect training and precision. If I made the Gaussians too small, the models sometimes struggle to learn to find them at all, even with weighted veloc. If I make the Gaussians larger, the model learns quickly, but then struggles to precisely pinpoint the peaks. So I tried a couple sizes and settled on a Gaussian size that's roughly this big in the image, and it seems to work the best for our model. To improve the training process, we can do some profiling, which lets us see which parts of the training process takes the longest. I saw that loading input images was taking a really long time, mostly in file I/O and pre-processing of PNGs for training. One optimization there was to turn our folders of images into a TensorFlow TF record dataset format, and also pre-bake some of the pre-processing steps like loading a PNG to a numeric array. Then I also played around with different batch sizes to fit well with my GPU in terms of preloading between training steps, such that it uses about as much of the GPU memory as I have available. I found small batch sizes of around 8 to 16 worked pretty well for training. I'm noticing the model sometimes gives up on heat maps or segmentations and just predicts no chessboard the entire time. You may come across this type of problem in segmentation models when using a default loss function such as the mean squared error. And I think the reason for that is the loss function tries to reduce the overall error down for all the pixels. And in our images, the number of chessboard pixels is much lower than the background pixels. So the easiest thing for the model to learn is to just guess background for all of the pixels. And this is called a local minima, and it's even worse for heat maps, which are just tiny Gaussian islands in a sea of black. So the first step is to modify our loss function to handle this weight imbalance. We use a weighted mean squared error here, as well as for the heat maps. Here it weighs the loss contribution of positive chessboard pixels more than the background. By using this weight factor, the model is penalized more for missing chessboard pixels or corner pixels. I'm also noticing that the model struggles to decide which heat map channel corresponds to which corner. Since we don't care which corner is the first, as long as they go around the chessboard in order, we'd like to train our model with a loss function that is rotationally invariant to the start corner. I also looked and tried out a couple other loss functions before settling on the simpler ones. Each of these have some qualities that can help refine the final precision of the heat map peaks. Mean squared error seems to struggle to do final refinement, but the mean absolute error works a little bit better there, and I think the adaptive wing loss is probably the best. I did a little side look into a type of block called a CoordConv, which tries to integrate spatial position as extra channels in a layer. This didn't seem to work that well, and some of the papers I read were a bit critical of this approach, but it seems like it could help at some point. I also had a look at residual blocks, which adds the input to the output so that the block is learning a difference instead of having to also pass everything else along. For such a huge impact in the ML community, it's a surprisingly simple code change. Training results seem about the same. There's supposedly better gradient flow, but I'm not really seeing much of a difference. The papers suggest that if a model is a bit too simple, then a residual block won't have much impact, so perhaps that's what's going on over here. I've been really interested in this concept of attention used by LLMs, which is all the rage nowadays. The paper "Attention is All You Need" is a seminal one from the last decade, and I want to see what all the fuss is about. I watched an amazing video by 3Blue1Brown on attention for LLMs. You should check it out too. I think it did a great job of explaining how attention works for text-based models. I'm interested to see how this might work for images. I'd like the model to pay attention to regions of the image where the chessboard and corners are, and pay less attention to parts outside. The UNet++ already does this to a degree, but perhaps these attention blocks could optimize this logic in a way similar to how CNNs optimize our DNNs in an image. Looking at the paper, one way to implement this is as an attention gate block that we'll replace some of our skip connections with. In the code, we'll add this new function block, and the idea is that it'll learn a sort of mask based on an input. In this case, the lower resolution, higher spatial context skip connection, to apply as a gate to the same level fine detail skip connection. Essentially, lowering the value of connections is not paying attention to. But let's not take their word for it. We can actually look at this mask since it's essentially an image. So let's start training and plot out what this gate looks like for some inputs. Wow, it seems to work really well. You can see where it pays attention and ignores the noise nearby. There seems to be a slight distance scale issue, but this is the new best. It's a bit slower than just UNet++, but here I think the improvement is worth it. It's just so cool to see how the model is learning to pay attention to certain parts of the image, just like we humans do. Normally, these sorts of in-between stages have tens to hundreds of dimensions, which I can't intuitively visualize in a meaningful way. So having this attention gate directly shows what it's doing, just like a Photoshop mask, and it's so awesome to see. I feel like I can understand and see what the model is trying to do more directly now. It's so exciting to see the effects of different model architectures visually side by side. Finally, we're at a point where it looks like Keypoints do the best job so far of getting chessboard corners. In previous videos, we'd have to use computer vision to fit a polygon to the segmentation mask, and getting OpenCV running in the browser, it actually takes a couple of milliseconds to do, and it didn't handle noise very well. Looking at our live ML model, it's really interesting how it predicts where it thinks the corner might be, even when blocked. Writing a handcrafted CV algorithm to do this took me literally years, and the model learned this in minutes. Look at how my hand blocks more of the chessboard until it eventually starts to give up. We can see it handles similar angles to what the synthetic dataset had. Once the angle gets too steep, it can't find the board anymore. I had another synthetic dataset with steeper angles, but I found that while it did a little better at those, the overall quality of corners and boards got worse. So there's a trade-off that perhaps an even larger dataset or model could overcome. I've made this model available as a live demo app to try it yourself. The link's in the description. I'm tempted to do a future version that finds pieces too, like we did in a previous video. From here, there are many directions we could go. Part of me still wants to get even more precise with the corners, as right now, it would still require a final computer vision refinement step. But that's supposedly a smaller and easier problem. Or we could use my previous approach too. Or we could design a tiny refinement model for just this step, sort of like the hourglass architecture. I did do a quick and dirty CV refinement step before that looks for the X corners around where it thinks the chessboard is, and then tries a ransack fit to that. And the concept's sound, and when it works great, but sometimes it chooses poorly. And even when it works, it's adding several milliseconds, which is almost halving the FPS of this model. So this doesn't really seem worth it yet. I think it's possible a bigger or better architecture model might get there directly, but pose optimization is a tough problem, and I'm pretty happy with where we're at already. You can see even state-of-the-art pose estimation suffers at sub-pixel accuracy for people. Another idea is SSD designs like CenterNet or CornerNet, which have layers for the XY keypoint offsets. I did an initial foray into this without much luck, but I think this is one of the better directions to go for future architectures. Another thing is all of my models are running on video frames independently. It might be interesting to implement a long short-term memory type LSTM model to have temporal consistency over multiple frames. This will make it a lot smoother too. Of course, classic CV approaches like the Kalman filter or Lucas Canade tracking are great options here too, but we've already done that in the past. This has been quite an interesting journey so far. Thanks for coming along, and subscribe to let me know if you want to see more videos like this. Leave a comment if you tried out the demo, and if it worked or if it didn't. A viewer asked me about possibly tracking a whole game from your phone and having those moves pass into Lichess or something. And I think I've seen some partial demos that do that out there, so I might try and make a demo like that in a future video. We could simplify the problem for just one kind of chessboard or like the more classic Staunton ones, and just let's assume some very simple lighting. Let me know if you'd be interested in that. Anyway, thanks for watching and see you next time.